Hi guys, welcome back to the Unity Shaders course. In this chapter, we're looking into render pipelines. A render pipeline, sometimes also known as graphics pipeline, is a sequence of steps a GPU takes to transform a 3D data like lights, textures, models into a final 2D image which we can see on the screen. So a 3D scene data will become a 2D frame. This process is happens so fast because this happens at least 30 to 60 times per second for getting a smooth real-time experience. So generally, the render pipeline has many stages. There are five core stages are there. So we have an application stage, geometry processing stage, rasterization, pixel processing, merging and or blending, then the out, that is 2D frame. So in the input is a 3D data. The 3D data contains everything inside that a scene. Okay, like models, structures, everything. Okay, in the initial stage, the application stage, CPU prepares the data. So which data needs to go to the GPU, which data is processing by the CPU. So this type of division is happens at the application stage. It is set a stage for the GPU to process this complex graphics rendering. So this application stage is basically a CPU bound process, and the later stages are all GPU bound process. So in a processing stage, the GPU receives the data from the CPU, mainly the 3D coordinates of the objects, and this geometry processing stage converts the 3D coordinates into a 2D space or 2D coordinates. For example, in this picture, we have a 3D cube. And suppose this is a camera. Okay. So we are seeing from this side, from the left side of this cube. So based on this viewing angle or this perspective angle, suppose if we draw a plane here. So what are the vertices we can see from this side? Like these are the four, let's say these are the four vertices we can see from this side. These four vertices are drawn into this plane. So we get a 2D square type of data. Actually, these are actually two triangles because this processing is happens at a triangle levels. So it's actually two triangles. So after that, we get uh, two triangles, one triangle like this and another triangle, for example, like this. So this is the first stage. It is called the geometry processing stage. In this thing, we convert a 3D object into a 2D frame using some perspective technique. The next step is the rasterization process. The rasterization process determines the pixel on the screen. So now we converted a 3D coordinates to 2D coordinates. We have that data, and that data is given to this rasterization stage. Okay, suppose this is our screen. Okay, our screen have many pixels, so each one box is a consider each one box is a pixel. So we want to draw this 2D image into the screen. So we need to know which pixel we need to activate in order to draw this 2D image. That process is happens in this rasterization stage. So we have the 2D coordinates. We only have the 2D coordinates. For example, we have let's say um, three three plus three, maybe six coordinates are available, and we draw these six coordinates based on this. Um, I'm roughly drawing like this. So we have a we draw a chord from two triangles. We have a this for these coordinates. Then we draw a lines between these coordinates. And applying some rasterization algorithms, we try to fill each um, each pixels. So we fill this pixel, this pixel, this pixel, and every time we fill this pixel, so that we will get a, a 2D shape. So this process is called rasterization. So we are effectively converting a vector shape into a grid of fragments. For example, consider this as a fragment, this pixel. So we are converting this 2D vertices into a collection of fragments. Now we have a 3D data converted into 2D, then we have a list of fragments. And this list of fragments is sent to the pixel processing stage of the stage. So here we go through each fragment. For example, this is our fragment. We go to the each fragments in this data and try to apply various colors and textures based upon some data. Okay, so now we get the coordinates, the position in the screen, and also the color of that fragment or pixel at that position. Now we send that data to this merging or blending stage. Here we combine all these fragments. Suppose we have several fragments in this stage. We combine this everything and then make sure we create a one single 2D frame and we put that inside a buffer. And this buffer is send it to our screen. Need to know why we are using such a complex render pipeline. So the idea is that this graphics processing, that is converting everything from a 3D to a graphics or a 2D image type thing, is very complex process. And this um, render pipeline helps to mainly to break down this process. So a very complex process, we break down a very complex process into a simple stages. Okay. And another important thing is that by breaking down this complex process, we are actually make way for parallelism. So this parallelism is effective, or we can utilize this parallelism property using the GPU. So GPU have this parallel processing capability. So by break down this complex process into various stages, we can apply this parallelism. So for example, we see in this thing that we have a vertexes, that is the main data, and the vertices is converted to 2D, then converted to fragments, then apply the colors. So each vertices have goes through various modification and transformation and applying various type of logics. So so let's say, for example, in this particular image itself, we have 6 vertices. So we can parallelly compute those things in 6 parallel ways. So we can utilize this GPU. The GPU can do this type of parallel processing very fast. And another important thing is that by breaking down this complex process into various stages, we can control it very easily. By controlling it easily, we can we can have more creativity. For example, we said that this application stage is basically a fixed type of thing, and rasterization is also it's part of the application. The users doesn't have that much of control in these cases. In the rasterization and the application stage is that much of control. So basically, the programmers or artists can have more control in this stage and this in this stage. So this shaders are mainly comes in these two stages, the geometry processing stage and pixel processing stage. So the render pipelines provides the way of the shader programming. So if there is no render pipeline, there is no shader programming. Okay, the power of the shader comes in this particular aspect. So we need to know what type of render pipeline we used. historically. So initially, we have a fixed function pipeline, which is actually a hard-coded type of pipeline, and which is hard-coded to the GPU. So the programmers or artists doesn't have that much of control here, and very capabilities are very limited because it can have all much that much processing capabilities because it is fixed function, and it has very few limited set of features like multiplication, adding, and that much of very limited set of processing capabilities also there. Now, by having this render pipeline, we can add many more features. So that is one of the advantages of using the render pipelines uh, compared to this fixed function hard-coded type of um, this pipeline. And this render pipeline is, we can say that render pipeline is more like a programmable type of render pipeline. Old ones are fixed one, we cannot have any control. These are programmable so that we can have more control, more creativity, and it have more feature set. So the programming, the shader programming, the shader programming is the way to program all the pipeline. We have many languages are for that, GLSL and HLSL. These are the shader programming languages. So now you need to know what are the limitations of this render pipeline. Three major limitations of the render pipeline is, first one is the based on the transparency. The second one is global illumination, and the third one is aliasing. I will briefly explain what is this thing. I plan to do a separate video, not a part of the course, separate video on each one because each topic is its own very depth. Each topic is very complicated. So in this transparency type of thing, um, for example, if I take this Unity code, we can see that there are several planes which have a transparency effect. For example, this plane, and these planes have a transparency is added added to this material. Okay, so in this type of transparency type of things, it is very difficult for the this graphics engine to determine what is the actual pixel value, what is the actual color, or which what is the order of this pixel to render. This type of things is very difficult in this case of um, a render pipeline, because in the case of render pipeline, it renders objects one by one. Maybe the render pipeline renders maybe the this plane first, then do this plane first. But the problem is that we need an overall idea, because once we look from in this direction, we are not seeing any separate plane. We are seeing a single 2D image which have multiple transparency, and we don't know which pixel has transparency, which color is using that. So this type of transparency makes problem. This problem, we can also say that this is an order independent transparency problem. Okay, I will explain more in the later topics. So another one is global illumination. So global illumination is that the fragment shader calculates the pixel's color based on the lights that directly hit it. It doesn't care about the light which is bounce off from one object to into the another one, or indirect lighting. It doesn't care about the indirect lighting, or we can say that the global illumination. So in order to achieve this realistic global illumination, or in a real time situation, we need ray tracing or light mapping type of techniques. In this render pipeline, we are using rasterization. It doesn't have this capability of this indirect type of lighting. That is one of its difficulties. Another limitation is the aliasing. So we know based upon this thing is that each 2D have this when after the rasterization, this 2D coordinates is converted to fragments, a collection of fragments. So once if we draw a line like this, so it becomes these fragments are uh, is actually lit, and this is actually create some sort of a jagged type of appearance. Like um, if you draw a line, and the line is like after isolation is like this, we have some jagged structure is there. This is called aliasing. So and this creates some problems, some quality issues after isolation, because we are converting an analog type of data into more of a digital type of data, a discrete type of pixel. So that is it is very difficult to create a very smooth type of line after rasterization. There are several techniques, a very anti-aliasing technique like MSSA, FSXA, TIS, that there. But this is one of its problems. These main problems are all related to the um, um, rasterization and how the objects are rendered. So it's basically about the how these render pipelines are structured. Okay. Next thing is in the Unity game engine, there are three type of render pipelines available. One is built-in render pipeline, and there are two pre-built scriptable render pipelines are there. One is URP and another one is HDRP. The main important thing is the scriptable render pipeline. In this scriptable render pipeline, uh, it is a C sharp programming based scriptable render pipeline. So the programmer can customize the render pipeline, how the lighting and post processing effects are handled. Everything can be customized and controlled through a C sharp code. So before we understanding the render pipeline, we need to understand there are two different strategies in render pipeline. One is called a, a forward render pipeline, another one is a deferred render pipeline. So the forward and deferred type of render pipeline is based on how and when they calculate the final color of a pixel, especially when multiple lights are involved. Forward rendering is a traditional, more intuitive type of approach. It calculates the final color of each object in the scene one by one, and for each object, it considers all the lights that affect it. For example, we have a 3D scene, and we have two objects, and we have multiple lights. So this is a screen, a 2D screen. So in the case of a forward, we have two objects, one and two, and for each objects, we calculate the lights from each source and finally calculated the color of that particular object. Then we take the next object and again do this calculation. So for every objects, n number of objects in the scene, and there are y number of uh, light sources. So n times n, y are the number of times this forward render pipeline will repeat this process. So it's very performance intensive, but it can handle transparency and the anti-aliasing. The next strategy is a deferred strategy. In the deferred strategy, it's actually quite opposite type of the forward rendering. It first figures out what the scene looks like without any lighting, and then applies the lighting in a single efficient pass. So instead of drawing object to the screen with their final colors, the GPU renders the scene's data into a texture called the G buffer. The G buffer stores all the information about each pixel, like albedo, normal, depth, smoothness, everything. At the end of this pass, there is no lighting, just set of textures containing all the surface information of every visible pixel. The next stage is the lighting stage. So in the first stage, we create a G buffer. In the second stage, we're creating the lighting pass. So now the GP ignores the 3D models. Now it considers only the light in the source. For each light in the scene, the GPU draws a shape representing the light's volume. Example, a sphere for a point light. So here there is a point, and this is a sphere corresponding to the that particular light. For every pixel on the screen covered by that light shape, it performs a single calculation. And based on this particular calculation, it added that the light of each pixel into a separate texture called a lighting texture. A texture called a lighting texture. And this process repeated for every other lighting objects. Since all the geometry information is already available in the G buffer, so it's this process is incredibly fast because the rendering is proportional to the screen size, the overall screen size, and the number of lights. So it's almost it has less number of iteration compared to this thing. If a scene having more than thousands of objects, which is quite natural in any game, then this forward type of things is more uh, not efficient. But the defer type of thing is efficient when there is more number of objects, because in this calculation they doesn't care about the objects, they only care about the light and the um, screen size. But the problem with the deferred thing is that we cannot calculate the transparency and the anti-aliasing. It is difficult or that much good in the case of a deferred type of thing.